Quantitative. Now instead of doing hypothesis testing for proportions, we're doing hypothesis testing for population means. Claim about the population means. The same concept applies. The same concept as with population proportions applies. Anyone can make a statement about a population mean. Anyone can say that someone can argue, well, I think that professional athletes get paid too much. Someone can go, no, they don't. They only average $12,000 a year. And they can make that claim, but they won't necessarily have evidence to be able to back up their claim. So we've got to have a way to test someone's claim that deals with population means. Okay, so same thing as with the last, with categorical. We've got the null hypothesis. It's written as H null. The null hypothesis is still written H null. It's the numerical value that represents the claim. And it's written like this. The null hypothesis is mu equals mu null. So if someone walks in and says the average NFL player makes $12,000 a year, we're not testing the entire population, we're testing their claim. So we're going to let their claim be the population. We're going to say that our test is going to support or reject their claim. Just like with categorical data, when you start off, this is assumed to be true. You always start the test giving the benefit of the doubt. Okay, let's just say it is. Let's just say that it is $12,000. And then you run your test accordingly. If you want to say, I believe that it's more than $12,000, then you run a one-tail test. If you want to say, I just believe it's not $12,000, you run a two-tail test. Of course, we still have the alternative hypothesis. Same as with categorical. It's the rejection of the null. It's the rejection of the null. And it's written as H sub A. It's the rejection of the null. There's three ways to reject the null. There's three ways to write this. You can say the alternative is mu does not equal what's being claimed. And if that's the case, it's a how many tail test? If you're saying it's not equal to, it's a two-tail. What that means is you're leaving room for the fact that it could be statistically significantly higher or lower. You're saying, I don't know if it's 12,000, but I think it's different than 12,000. So it could be a lot more than 12,000, it could be a lot less. So it has two tails. Okay? And in between those two tails is the fail to reject region. And on the outside of that is the rejection region. The second way we could write this is we could say, we don't think that you're just wrong. We think that it's actually, let's give it more specific. We don't say, well, we think that it's actually not 12,000. We think that it's less than 12,000. So you're making a claim that it's less than what's being stated. So if someone said, okay, well, are you still doing the science fair project with the plant growth? Yeah. Okay, so John's doing plant growth based on soil types. So he could say mu equals, and whatever value he chooses to put here could maybe be the average potato production weight-wise or height-wise of the controlled group using the controlled soil. And then you'd say, okay, did my soil that was fertilized with this much every week, was it statistically significantly better or worse, or the other one would be, is it statistically significantly better? And then you collect both your samples and you can do a comparative study. So this is a one-tailed test in which you're only interested in data that is less than. If you're trying to say, hey, you're wrong, I think it's less than 12,000, you go out and collect a sample, and the sample gives you an average of 28,000, you definitely have no evidence to support your claim. That's actually less than. So that's a one-tailed test, and then we have the opposite of that. Is we can also have the alternative is, well, no, I believe mu is actually more than that, making it a one-tailed, in which you're only interested in data that is greater than. And once again, if you're to go collect data and you said, I think it's more than 12,000, you go collect data and your data says it's actually, based on our data, it's 6,000, you have no evidence to support your claim at all. So therefore, it would be a redundant study. Yes, sir.
Would we be using t-shorts?
We're going to, that's right. Yeah. Yeah, because we'll have two subcategories, just like with the other. Yeah. So, yeah. So that's our hypothesis, and then after our hypothesis comes the test statistic. That was the number of standard deviations our data is away from the population mean. This is going to be the number of standard deviations our data is away from the claim about the population mean. Just like with categorical data, we've got two versions. Okay, so we have a t-test or we have a z-test. Just like we had one proportion z intervals, that was for categorical, and then we had z interval and t intervals, that was for quantitative. We have t-test and z-test. When does t-test get used? This is used when sigma, which is the population standard deviation, what? Is not known. And then the z-test will be used when the population standard deviation is known. Same concept. T-test, z-test. One's used when you have the population standard deviation not known, and one is used when the population standard deviation is known. The formula for T. It's always our data, which is the sample mean, right? Minus, and typically it would be minus mu, right? But now it's going to be minus mu null. Because up here at the beginning, we said we're going to let mu be mu null, right? And then it's over the standard error of our data, which has the formula S sub x over radical n. It's the same formula we had for t in the last section. Your sample minus the claim divided by the sample standard deviation. Over square root of n. And once again, guys, S sub x over square root of n is just the formula for standard error. And then if sigma is known, then the formula is x bar minus mu null. But instead of using the sample, we'll use the population standard deviation. It's the exact same concept. But if you know the population standard deviation, it's better off to use that and use a z-test than it is to use a t-test.
Why don't we just use t-scores all the time?
Because t is not exactly normal. Remember, t is a corrective model that makes it approximately normal. If we know the population standard deviation, we can use a normal model, which is more accurate.
Okay.
But the higher we go in the chart, the more accurate it is.
That's correct. Yeah.
So if you have really big numbers,
It's not going to make a difference. Yeah. Because once you get to 1,000 people, T critical and Z critical are the exact same number. So once you get to 1,000 people, those two will be the same. All right. So let's go through an example. Obviously, Z test is a little easier than a T test. For the sake of this, and I'll show you why, because we've got to be able to work the chart backwards. But we're going to do one example of the Z test and one example of the T test. That's the end of the notes for statistics.
What?
We have two examples. One example of a Z test, one example of a T test.
In general?
That's the end of the notes.
Oh,
Well, we're going to have reviewing for the chapter test and that kind of stuff, but in terms of new material, we have two examples.
I've never been so happy to day.
It's finally.
It's kind of sad now.
No, it's not sad at all. This sounds celebrating.
Now we get to do fun.
College algebra.
That's apparently a lot easier than statistics. Beginning of the year.
Yeah, I know. We think last time.
And we still finished early.
The curriculum is not pushed too hard this class. Calculus, I have to scrap like half a chapter of material because it's, and we still push to get that on time. It just depends. A group of 10 students have an average weight of 170 pounds.
Oh. Okay. I was really confused. Like, wouldn't that be a lot higher than oh yeah, average.
They came from a population with a standard deviation of 17 pounds. Right there tells you it's a what kind of test? It's a, they came from a population with a standard deviation of 17 pounds. It's giving you the population standard deviation. It's a Z test.
Oh.
So that tells you, I mean, this line right here, what I'm getting ready to highlight in yellow, tells you that it's a Z test.
But if it didn't say population standard deviation, it'd be a.
So if it said a group of 10 students have a mean weight of 170 pounds and a standard deviation of 12, then that's just corresponds to just that 17 students. So then it's a T test.
What?
If instead of saying that they came from a population with standard deviation of 17 pounds, if it said a group of 10 students have an average weight of 170 pounds with a standard deviation of 12 pounds. When it's stated like that, that means that that 12 pounds just has to do with these 10 students.
So it has to say it's for the whole population.
Or it has to say from a large, this comes from a larger group or some wording like that, yes.
So Z test whole, T test sample.
If you know just the sample, correct. Okay. I believe the average weight of the entire population is 180 pounds. Is this an acceptable claim? A group of 10 students have a mean weight of 170 pounds. They came from a population with a standard deviation of 17 pounds. I believe the average weight of the entire population is 180 pounds. Is this an accurate claim? So, basically what we're saying is I could come in and say, okay, I believe that the average student weight at Western Heights is 180 pounds. And you'd say, okay, I don't know if that's an accurate claim, so I'm going to go out and ask 10 people their weights, and I got an average weight of 170 pounds. Now, the only way you can know the population standard deviation is 17 pounds is if you knew everybody's weight. Doesn't happen that very often. Okay, so t-tests are more popular than z-tests for that reason. Just like doing t-intervals happened way more often than z-intervals when we did that worksheet. Because very rarely do you know the entire population, unless you're talking about something like the ACT or some standardized value that's been taken across the entire nation or across the entire state. If you're conducting a survey about your own subpopulation, you're not going to know the whole population standard deviation. But in this case, we magically know that. So, first thing we're going to do, step 1 is the significance level. Step 1 is set your significance level. It does not tell you what the significance level is. So, we're going to just do alpha equals 0.05. Step 2 is come up with our hypothesis. The null. You assume that the claim is true. What's the claim?
That's the average population weight is. Sorry.
The claim is
Oh, dang it.
mu is 180.
Oh, why did everyone laugh at me? I don't understand.
I think it was just the fact that you got slightly tongue-tied. I believe that the average weight of the entire population is 180 pounds, so we're testing, is that an accurate claim? So we're just going to say, okay, let's assume that whoever's making that claim, let's go ahead and just assume that they're correct. Does anywhere in here say, does this claim seem to be too high, or does we believe it actually is lower than this? No, it just says, is this an acceptable claim? So we're going to treat this as, our alternative is going to be, mu is just not equal to 180.
Oh.
If it said, does this seem to be too high? Then it's asking, is this too high? So then you'd be testing, is mu actually greater? If it asks you, does this seem to be too high, you'd be testing, is mu actually less than? Does that make sense to everybody? So then it would take it from a two-tail and turn it into a one-tail. But right now, it doesn't say anything like that, so we're just going to treat it as a two-tail test. Which a two-tail test is stronger anyways, because at the very end, you're going to take your p-value and you're going to do what?
Double it.
You're going to double it. You're going to times it by 2. Okay? So if it works for a two-tail, it'll also work for a one-tail. So, our test statistic, we've already identified that this is a z-test. So we need to be able to fill in this formula. Sample mean minus the null, which is the claim, over the population over radical n. All of that can be plugged in. What's the sample mean? 170. What's the claim that's being tested? 180. What's our population standard deviation? 17. And what's our sample size? 10. So we just fill all this in. 170 minus 180 goes on top. That's a negative 10. On the bottom, we have 17 over square root of n, which is square root of 10. Anyone have what that is?
Altogether.
Altogether.
136.5.
You gotta make sure you type in the top, type in the bottom, divide the two answers. Hello. Yes. Okay. All right. So anyone? Negative 1.86. negative 1.86. Alright, so we come up with our test statistic. The next step is we come up with our p-value. So we're going to draw this picture. Negative 1.86, is that below or above? That's below.
But when did you start recording?
I've been recording all that.
Yeah, we go for 20 minutes.
Negative 1.6 is below. We're testing a what kind of test? A two-tailed test. So that means we have to include the negative and the positive version. The fact that we're doing a two-tailed test means we have to include both tails. So we include negative 1.86 and positive 1.86. Which of these can we use the chart to find the p-value for? We can find the p-value for negative 1.86. We go to our chart, we find negative 1.86. We get 0.0314. Everyone good? But then we've got to take that answer and do what?
Double it. Plug it.
Multiply it by 2. 0.0628. We times by 2 because we've got a two-tailed test. Then our decision. We take that p-value, 0.0628. We compare it to our alpha, our significance level. Is it more than or less than?
More than.
It's more than. That means that the probability of us saying, hey, you're wrong in your claim, and actually them being right in their claim is more than 5%. That's too much, based on the significance level. So what we're going to say is, we fail to reject the null. If your p-value is more than the significance level, you fail to reject the null. That does not mean you're agreeing with them. That just means you're saying, I don't have enough evidence to disagree with you.
Are you able to pair back?
I want to talk about that in just a second. Yes. Yeah. You can change alpha. Yeah. Yeah. So that's a good question. Yeah. Why don't you? So let's say we're back and say, okay, we want to change our study. Instead of doing alpha equal 0.05, let's do alpha equal 0.1. Instead of doing a 95, let's do a 90. Or instead of doing a 90, let's do an 80% basically confidence interval. If this was 0.1 instead of 0.05, we would, instead of saying fail to reject, we would say reject. So then we would just say at an alpha equal 0.1 significance level, we reject.
It's all how you choose to show
It's
your.
all in the fine print. It's all relative. All right. So that's our decision, and then here's our report. Based on our sample, n equals 10. If you fail to reject, then you did not have enough statistically significant evidence.
Good job.
So you say there is not enough statistically significant evidence
Then we just raise it. Okay.
Oh yeah. Same.
to reject the claim the entire population average weight is 180 pounds. At the alpha equals 0.05 significant level. Parentheses, P equals 0.06, which is greater than 0.05. The 28 becomes redundant. The 0.0628 mean nothing because if 0.06 is greater than 0.05, 0.0628 is also greater than 0.05. Now, and that's how you finish this report, guys. Now look here. We treated this as a how many tail test?
Two-tailed.
Two tail. We treated this as a two-tail test. and we got a fail to reject. If we would have multiplied this p-value by 2, our p-value wouldn't have been 0.06, it would have been 0.03. Does that make sense, everybody?
Yeah.
Is that less than 0.05? Yes. So instead of doing it as a two-tail, if we would have done it as just a one-tail, instead of doing it as a two-tail, if we would have just done it as a one-tail, we would then be able to say what? Reject. So basically what we would need to do is we need to change this to just less than. Does that make sense, everybody? So if we change this to just less than, what we could say is, based on our sample, n equals 10, there is statistically significant evidence that the claim is incorrect and that the population is actually less than 180 pounds. Shannon, does that make sense?
Yep. Can you go back down? Okay, try this. Go back down. Sorry, we still have statistics.
Oh, yeah, we have multiple statistics now.
Oh, thank goodness.
No, not